Okay, Assalamualaikum warahmatullahi ta'ala wabarakatuh, and a good day to everyone. Okay, I'm so sorry that I wasn't able to have a synchronous class with you guys, so I'll just give you a recording of the next topic. Okay, so let me just play the slides. Okay, so what we are going to look at today is on continuous humidification processes. Mainly, we will look at how to design a cooling tower. Okay, so actually, this cooling tower, I think almost all chemical plants will have cooling tower. Okay, this is because you will need this water to cool down or to do some heat exchanging process with turning a stream or cooling a stream down to the temperature that you would like for your operation in your plant. Okay, so how does it work? Okay, actually, a cooling tower works on using a concept of evaporation. Okay, when you evaporate the warm water, and the warm water then comes into contact with unsaturated air, so there will be latent heat of vaporization given off, and this will in the end cools this will cool the water in the cooling tower. Okay, and then the water in the cooling tower can only be cooled just down to the wet bulb temperature. So I believe you have learned about wet bulb temperature, right? Before in I think in transport processes, and also in energy balance. Okay, when you design the heat exchangers, and in this process, what we assume is there will be only small amount of water lost. Okay. And then, the first kind of tower that we will look at is a pack tower. Okay. So as I said earlier, if you look at this, I hope you can see my cursor. Okay, if you look at this diagram here, the water from the cooling tower is used for heat exchangers mainly, but there are also some other usage of the cooling, the cool water from the cooling tower, but mainly it's always for the use in your heat exchangers. Okay, so this is how you what do you call it, display a diagram or a schematic of a cooling tower. Okay, so in this diagram you can see that warm water flows countercurrently to an airstream. So that means the warm water will be sprayed down. Okay, it will be sprayed down into the packing. Okay, and then you will have air flowing upward because you want the air to be in contact with the warm water flowing down, and you will make when the warm water meets or in contact with the packing, and it will cascade down, and then in this process, when they are in contact, there will be some heat transfer occurring, and there will be changes of temperature because of the change of phase of the water. Okay, and then there are two types of cooling tower. First one is natural draft, and the other one is forced draft. Natural draft means you don't have a fan forcing the flow of the air. You will just use natural draft, but in a forced draft you will be having some fans to force the airflow into the direction that you want, and the process is adiabatic, and the water can be discharged to the river or recirculated and reused. Okay, because sometimes you will produce wastewater that is high in temperature. So before you release it to the streams, the rivers, you need to bring the temperature down to comply with the Department of Environment, what do you call it, compliance standard values. Okay. All right, so this is how a natural draft water cooler looks like. So you don't have a fan, and it's usually very big in size, and this is how it looks. And this, oh, I don't have a picture of a forced water cooler, but I think the shape is very much different from the natural draft water cooler and the forced draft. Okay, I will try to put in another diagram or photos to show you how a forced draft cooling tower looks like. Okay, so let's go to the next slide. So this is how the process that I explained to you earlier, and how you get the humidification process happening. Okay, so in the process of humidification, there is actually a transfer of water from the liquid phase into a gaseous mixture of air and water vapor up here. So you have the water here, it will be transferred into the space above the surface of the water, which is occupied by air and water vapor, because this water here has changed or has turned into vapor. So air is gas, water vapor is also a gas phase. So actually this water from here, because of its volatility and also the condition of the space above the surface of the water, it will evaporate and change into water vapor. And because the air, which is initially dry, and it meets with the water vapor from this water body, and in the end, as a result, this air will be humidified because it contains water vapor in here. That's why it's called a humidification process. Okay, so meanwhile, for the opposite of humidification is actually dehumidification. I think from the term itself, you can make a definition of it, which is the opposite of humidification, where the water vapor is transferred from the vapor state to the liquid state. All right, so let's look at the next slide. Okay, for you to be able to do the calculation and also to design the cooling tower, you will be using a humidity chart, and you have to be good in reading your humidity chart. Okay, I think from the last batches of seniors previously, they all told me that you have been taught on how to read a humidity chart, right? So I hope you still remember from your other classes that use humidity chart, maybe in transport processes, okay, or any other classes. Okay, but I will still show you on how to read the humidity chart briefly. Okay, so the humidity chart actually will show the properties of the air water vapor mixtures. Okay, you have do you remember that diagram before, where you have the space above the surface of the water? It's actually a mixture of air and water vapor. Okay, and the properties are actually covering the properties at 1 atm absolute pressure. And the axis, if you look at the axis here, the y-axis is humidity, and the x-axis is the dry bulb temperature. Okay, so I hope you still remember. So let's see on how to determine the humidity at a wet bulb temperature of 20 degrees Celsius and a dry bulb temperature of 30 degrees Celsius. So Dry bulb temperature is the temperature that you read from the thermometer. Okay, so that's called dry bulb temperature. Wet bulb temperature is the temperature that you read with the bulb of the thermometer wrapped in wet cotton or wet what do you call that, wet gauze, okay, or wet cloth. So it actually depicting or showing or representing the maximum humidity that you can achieve at that particular temperature, dry bulb temperature. Okay, so that is what the wet bulb temperature is. So in this case, when you're given with the dry bulb temperature and you're given with a wet bulb temperature, you want to determine the humidity. What you have to do first is you draw a vertical line at the wet bulb temperature. First, take the wet bulb temperature, 20 degrees Celsius, and go vertically until you reach the saturation line. This is saturation line means 100% humidity. Remember what I told you before, that the wet bulb temperature is actually measured with a wet cloth around the bulb. So that's actually representing the maximum or 100% humidity. Okay, so that's why you draw the vertical line to meet the 100% humidity or the saturation line. And the next step that you have to do is to draw a line starting from the point of what do you call it, the point where this vertical line crosses the saturation line, and you will have to find the wet bulb lines that is parallel with all the wet bulb lines that you have in the chart. So let's say if your wet bulb temperature is around 15 over here, you go up and it will meet the saturation line over there, and you have to take your ruler and draw a I better annotate or draw something here. So for example, if you have let's have this in different color. Okay, let's say if the wet bulb temperature you have is 15. Okay, so that means it meets the saturation line over there, right? The saturation line meets over there. And then what you have to do is take your ruler and draw parallel to that wet bulb lines. So that's what you have to do for the next step. Okay, so next what you have to do is you have to draw a line vertically from the dry bulb temperature, and you determine where those two lines meet. Okay, so from that line what you have to read is the humidity on the y-axis. Okay, so that's how you read the humidity, which is in this case 0.0115. Okay, so I hope you still remember. And in the cases where you're given only with the dry bulb temperature and the percentage humidity, let's say you're given with a dry bulb temperature of 25, let's say, and you're given with 80% humidity. So what you can see, or what you can determine for your humidity is that it's 25 is over here. So you go up and then you meet the 80% humidity over there, right? And you can read the humidity here straight away. All right, so that is if you're given with a dry bulb temperature and straight away with the percentage humidity. Okay, so let's see, I think that's about it for the humidity chart, and let's see what we have. Okay, the other one or the other method to calculate humidity is when you're given only with dew point. Okay, so in this case, in the next example, you're given with a dew point of 10 degrees Celsius. So what do you have to do? You have to take, you have to draw the vertical line. Okay, you have to draw the vertical line here from 10 degrees Celsius, and because it's a dew point, okay, then what you have to do is just easily read the humidity on the y-axis, which is corresponding to the point where it crosses the saturation line. Because actually, when you have dew point is the temperature where the first liquid is formed from a water vapor. Okay, this is defined as 100% humidity as well, and or what we call a saturation point. So this is where the point of cross, where those lines cross each other, and you can straight away read the humidity over here. Okay, so in this case it's 0.085. all right, so that's how you read a humidity chart. And in your Jean Copley's book, you can find the humidity chart in figure 9.32 in the Jean Copley. So you will be using this humidity chart a lot, okay, in your exam, in your test. Okay, so you have to be really good in reading the chart. Okay, so now I will go straight into the theory and calculations for a cooling tower. Okay, so first, before we go further, I would like to introduce you with all the terms that we are going to use. All right, so now actually, the skill that you have been learning in the last topic, which is the mass transfer and how you calculate the mass transfer flux, and you calculated the interface values, right? So you'll be using those skills in the design of the design of this cooling tower. Okay, so let's go back to this. What is L? L is actually here. Okay, you look at L. L2, L1. Okay, so L is actually the water flow rate. The water flow rate starts from the top going downwards. Okay, that is for the water flow. And TL is actually the temperature of the water that's flowing from the top to the bottom. And if you see here, the L up here, we call it L2 because all the numbering and symbols are based on G, which is the gas flow. Okay, so G is actually dry air flow rate that comes from the bottom of the tower and will travel upwards. Okay, so we call the point of entry of the G as 1. Okay, so all symbols corresponding to this point will be denoted with a subscript of 1. Okay, so G1 is the flow rate of the air, TG1 is the temperature of the air coming in, and H1, H is the humidity. Okay, H is the humidity, and HY is actually the enthalpy of air and the air vapor mixture. Okay, the vapor is the water vapor. Okay, so you cannot be confused with between HY and H. Okay, H is humidity that you read from the chart, which corresponds to the temperature that you want to achieve. Okay, HY is actually the enthalpy of the air and water vapor mixture at those points. Okay, so if it's here, then it's for this enthalpy at this point. If it's HY, means that the particular point that you want to take along or along the height of the packed tower. All right, so MB is molecular weight of air. I hope you all know what molecular weight of air. Okay, this is general knowledge. P is atmospheric pressure. Z is the height of the tower. And the main parameter or variable that you wanna calculate or design in a humidification tower, or or more commonly called a cooling tower, is the height of the tower. Okay, so we're gonna learn on how to calculate that. Okay, so this is the equation to calculate that using the film mass transfer coefficient. You still remember, right? This film mass transfer coefficient will be represented by a small k. And this other equation is when you calculate that using the overall mass transfer coefficient, which is usually represented by a capital K. Okay, so K, this is the film mass transfer coefficient. This is the overall mass transfer coefficient. So G, MB, KG, A, and P are all constant. Okay, what changes are only the values in the integral. Okay, so the hard part is to determine this number and also that number. Okay, because this requires calculation of area under the curve. Okay, but you don't have to worry about this. These are all constant. Okay, so let's look at the procedure for you to calculate or to design a cooling tower. Okay, so the first thing that you have to do is for you to determine the humidity from the humidity chart with the given Tg1, which is the temperature of the air fluid coming in, and also the wet bulb temperature. Okay, so you have the dry bulb temperature represented by the Tg1, and you have the wet bulb temperature, and you have to find H. Okay, from that H, you can calculate the enthalpy, which is the HY. And this is the equation for you to calculate HY. If you notice, you will put the H1 you find from step number 1, and you will put in this equation for HY. Okay, once you get the HY, you will use the HY1 you calculated from step number 2 to calculate the HY2. HY2 is the enthalpy at the top of the tower. Okay, HY1 is the enthalpy at the bottom of the tower. So you have to know both. Okay, with a known value of G, known value HY1 from step 2, known value of L, CL, TL2, and TL1, you will be able to calculate your HY2. Okay, so actually the TL2, if you refer to the diagram before or the from the previous slide, you will notice that TL2 is actually the final temperature of water. Sorry, the temperature of the water flow rate, water flow that comes at the top of the tower. Okay, so this is the initial temperature, and you want to reduce the temperature to your target temperature of TL1. Okay, so this TL2 is actually the temperature the temperature of the water you receive from whatever process you have from or before the cooling tower, and this is the TL1 is actually the target temperature that you want to achieve from your humidification process. Okay, so the next step is to plot the equilibrium line. Okay, the equilibrium line that you will use is always the same, which is in table 10.51. I will show you in the example next. Okay, and you have to also draw a line from all the values of HY1 and HY2, and also TL1 and TL2 on the graph paper. I will show you how to do this, and then you will have to draw the operating line with the point TL1, HY1, and also TL2, HY2. And in the end, this is how your graph should look like. Okay, this is a graph of enthalpy of air water vapor mixture on the y-axis, and you have the liquid temperature on the x-axis. Okay, so TL2 being the initial temperature that comes into the initial temperature of the water that comes into your cooling tower, and TL1 is actually the target temperature. Okay, so when you plot, this is the equilibrium line you draw from the table 10.51, and when you plot the points TL1 and HY1, you will get this point. And when you plot TL2 to HY2, then you will get 2 points. In this case, you can just connect those 2 points to get this operating line, and the slope of this operating line is actually LCL over G. This is actually derived from the mass transfer equation as well. Okay, so next, step number 6. Okay, let me just enter. Okay, step number 6 is to plot several lines with that slope. Okay, this is where you will use the skill that you learned in the last topic, which is the mass transfer. You still remember, right? Okay, you want to plot several lines with this slope because actually you want to solve this part of the equation, which is HYI minus HY. So remember, you have been taught on how to calculate the interface values, so this is where the skill will be useful. Okay, so in this equation, HLA is actually the liquid phase volumetric heat transfer coefficient. It's a constant as well, and you can calculate the slope, okay, from all these constant values. So all these lines, okay, all these lines are actually having the same slope. Okay, so the goal or the objective is to get as much values of HYI minus HY, because you want to get this integral, right? In order for you to get this integral, you want to be able to get the area under the curve, right? So you have to plot this graph, 1 over HYI HY on the y-axis against HY values on the x-axis. Okay, so with that, then you will plot the area or calculate the area under the curve. So back to this. Okay, when you have the slope, okay, you can see here you have to draw at least maybe 6 lines in between TL1 and TL2 to get a good value for your area under the curve. Okay, so you have to obtain several values of HYI. How you obtain value of HYI? When you have this slope and you draw based on the operating line, you start with the TL. Okay, start with the TL, and then you will get to this point. Okay, and then with the slope, you will be able to plot the point M. So remember, what you have to put in mind, point P is always on the operating line. Point M is on the equilibrium line. So if you remember from our last class, point M is actually lower than point P, right? That's because the operating line is actually above the equilibrium line. Okay, there are in some cases of absorption tower, the operating line will be above the equilibrium line. So in this case, the operating line is actually below the equilibrium line. So that's why your point M is above the point P. But the concept is still the same on how you draw the line from the point P, which you get from TL. Okay, you can take any value, maybe using the same interval or any interval you like. Okay, so you start from TL1 and then you move to the right to TL2. So one example is when you take this TL, you will be getting the point P. From the point P, you will use the slope to find point M. Okay, and then you from the point M, you can determine the value of HYI corresponding to that TL that you take. Okay, so you have to do this several times. I recommend you to do maybe about 6 or 7 similar lines here for you to be able to calculate the area under the curve to solve this part of the equation. Okay, so once you solve this part of the equation, then you will be able to calculate Z from this equation. Okay, and all these are actually constants. All right. So that's actually how, I think that's actually, that's about it for you to calculate the Z. So let's see. That is when you use the film mass transfer coefficient. Okay, so remember you have 2 types of equation, which is using the film mass transfer coefficient, and the other one is using overall mass transfer coefficient. So let's see, how do you do this with the overall mass transfer coefficient with the capital K, okay? So you will do step 1, 2, 3, 4, 5, just like how you do for the method using overall, using the film mass transfer coefficient. Okay, so starting from step 6, it's going to be different. All right, so instead of drawing the lines here, okay, you draw the lines here to get the HYI. What you have to draw is only a vertical line from the TL values. Okay, so you can, for example, start with TL2, you go straight to the equilibrium line, and then you go to the left to read the HY2 star, which is the equilibrium temperature. And you can take several points in T on the x-axis for TL, and finally finish at TL1, which you start here, and then you go to the equilibrium line, and then you can read off the HY star. Okay, so then you plot the 7 values that you get from HY star. You will calculate the value of 1 over HY star minus HY. HY is the value that you get for the same temperature. Okay, so you actually have to do an extensive table for you to get all these values and for you to get the area under the curve for this part of the equation. And then finally you will put into the equation using the overall mass transfer coefficient, and finally you will get your Z. Okay, so I don't think that's very difficult. That's not that difficult, right? So I hope you can all understand. And the next part or the next slides will be we'll be looking at the example. Okay, so I'll just pause the recording for a while, otherwise this is going to be too long. So I'll just stop here first, and then I will record one more recording for the example. Okay, so you can look at this video first. I'll be sending another video which covers the example. All right, so for now, that's all. Stay tuned for my next video. If not today, I will post it maybe on Thursday. all right, for you to digest this first. So for you that have extra time or free time, you can go through the example on your own, and that way when we have class on what do you call it, on Thursday, you will have some idea on how to actually do this. Okay, so I am planning to have the class on Thursday synchronously. Okay, so I'll be seeing you live on Thursday for me to show the example. All right, so see you guys. I'll stop here, and I'll be sending this video in e-learning, so please download from e-learning, and maybe I'll post it in the WhatsApp group as well. Okay, so see you guys. Bye.